So I'm going to continue looking at our multivariable calculus and partial derivatives and different uses we can put them to. So remember last time we were dealing with the tangent plane to a surface. Talking how a function, this was last week. Sorry, I wasn't here on Monday, so I was at the dentist, but I'll be doing both of the lectures on Monday, this coming Monday, to make up for it. So to balance back out, you had Steve twice this Monday, you'll have me twice next Monday. So last time we saw a function of two variables. We looked at the surface defined by that function of two variables, and we looked at finding the tangent plane to the surface and how the partial derivatives with respect to the two variables, how they provide the slopes really of the tangent surface of the tangent plane in the x and y directions. And really we're going to keep looking at that now, and we're going to have some examples to work through in this session and keep looking at it, but in a slightly different manner. And just to remind you of something from last year. There was a way of taking, we showed you last year, a way of taking any function and producing describing the behavior of the function, say, close to 0. So the behavior of f close to 0. Well, what's your first stab, or what's your first guess at how the function is going to be behaving near 0? If you're only allowed to estimate it using a constant, which constant do you use? If I want to predict what the weather is going to be like tomorrow, the simplest prediction I can give really is just exactly what the weather is going to be like today. I know it's going to change a little bit, but with no other information, I just say it's going to be like it is today. So how should a function behave close to 0? Well, your first guess is that it will just take the value that it has at 0. Maybe it might change a bit, but that would be the first guess. But then maybe we'd allow a linear part to the estimation. And then we had that the coefficient of the linear part was the derivative of f evaluated at 0. Then we could let an x squared part into the estimation. Can you remember what the coefficient of the x squared? The coefficient of the x squared was the second derivative evaluated at 0 divided by 2. So this had a name. This was called the Taylor series for a function of a single variable. Okay, Taylor series. This was the Taylor series for it. It provided an infinite series which gave the value of the function in some neighborhood of 0. Sometimes, for certain functions, it was valid for the whole of the real numbers. For other functions, there was a radius of convergence, so it was only valid in a certain region around 0. The initial parts, if you take some initial part of the whole, it's an infinite series involving all the derivatives of f and all the increasing powers of x, but the initial parts provide the Taylor approximations, Taylor approximating polynomials, let's say. Taylor approximating polynomials to f. So the best way to predict f with the constant polynomial, with a constant, would just be to use the value it has at 0. It's a constant order 0. If you want to use a polynomial of order 1, meaning a constant term plus an x term, the coefficient you should use is the first derivative of f evaluated at 0. So this was order 1 approximation. The order 2 approximation then would be f of x is approximately, well, just what I've written there, f naught plus f prime of 0, x plus f double prime. The second derivative of f evaluated at 0 over 2 times x squared. This was the order 2 approximations. These are the Taylor approximation polynomials to f. Or it's also the term Maclaurin approximations are used when you're, that's a special term given to the, when you're expanding it around 0, and you're estimating the function close to 0. So what we want to develop is the equivalent thing for functions of more than one variable. Okay, this is the case for functions of a single variable. So we expect some similar result for functions of 2 or more variables, and it's bound to include the partial derivatives. Okay, and we've already seen the linear part. So linear, or the order 1 is also called linear approximation. It's a linear function, a constant plus x itself is a linear function. These other ones aren't linear, of course. They've got some kind of curve to it. So this, the order 1 is just approximating the function with a straight line. And this will be the best straight line that approximates it best close to 0. So we want to do the same thing for functions of more than 2 variables. And now there's some kind of theoretical-ish material presented here in this section, which I'm just going to jump over for the moment anyway, because really the thing I want to come to is this small increments formula. So the small increments formula this provides the linear approximation or the order 1 approximation to a function of, well, any number of variables. Linear approximation to a multivariable function. Now the way it's phrased in the book is we speak of delta f. But delta f is just the difference between the function f. I want to fit it in, make it match equation 1.58. So this could be a function of any number of variables. Sorry, let me just give a two variable one first. So we're going to speak of f of, let's say, a plus x and a b plus y. This is going to be the derivative of f with respect to x, evaluated at the point AB. This is going to be multiplied by the difference x, and the derivative of f with respect to y, again evaluated at AB, but this time multiplied by the difference y. Oh, and added in here we've got the constant part AB as well. So we're looking at the value of a function close to some base point AB. Sorry, this is approximately equals. This is the linear approximation to the function f. Okay. So we're looking at its values close to a base point AB. So x and y, if you like, are small variations off the base point AB. We look at the two partial derivatives, df and dx, evaluated at the base point. They are multiplied by the variations x and y. And then there's a constant term in the approximation as well, which is simply the value of the function at the base point. So writing delta f for the change in value of f, writing that for a plus x, f of a plus x and b plus y minus f of a, b. Then we get the small increments formula, which is given in the book. Okay, so the general small increments formula says that change in value of a function, change in value between the value it has at some base point AB and the value it has at some nearby point, is going to be approximately, well, you take the change in value of each variable, so that's represented by the x and y here, but writing it using this delta notation, we'd use delta xi. And that's multiplied by the partial derivative of the function with respect to that variable. So you take the partial derivative of the function with respect to one of the variables. That is multiplied by the change in value of that variable. And then this is simply summed over all the variables that the function has. Okay, so here was a case of just summing from I equals 1 up to 2, just going across two variables of a two-variable function. But in general, so this is the one in equation 1.58. Okay, this is the general form in equation 1.58. So what this is, it's an approximate expression for the change in value that the function undergoes when one or more of the variables of the function undergo a change. So delta xi is the change in one of the variables. So that's the change in the ith variable. And the df dxi is the partial derivative of the function with respect to that variable. Okay. And the partial derivatives are evaluated at the base point. So in this example up here, the base point was represented as AB. So the two partial derivatives got evaluated at AB. And the best way to see this happening is to jump in and look at some examples. And then I've got a problem for us to work on here in the class as well, to do it torus. Well, let's look at example 1.7 first of all. So 1.7 is about a way of measuring the force of gravity through the behavior of a simple pendulum. Okay, so a simple pendulum is like this, depicted in figure 1.3. The idealized experiment. You've got just a fixed mass at the end of a massless rod or a piece of string or something, and it's just undergoing small, gentle, smooth oscillations back and forth. Okay, swinging. So you pull it away from the vertical, and it just swings back and forth. Okay, and the thing that's making it swing back and forward is, of course, the action of gravity. If it was in outer space, you'd move. Analyze the physics of this, and I think it's kind of presented extremely fast in the footnote down there, but it's not what we're particularly interested in now. But you can go through the physical principles of how force relates to acceleration and so on, and you end up with this equation, or this approximation, that g, which is a measure of the force of gravity, or g is the acceleration due to gravity. So g is expressed in meters per second, say, distance per time squared. So g is the acceleration due for gravity, and out of the physical principles comes this approximation, that it should be approximately 4 times pi squared times L divided by t squared. Now L is the length of the pendulum, and t is the time taken for one full oscillation. So when it's of the oscillation. So t is the time taken for that, and L is the length of the pendulum. Interestingly, it doesn't depend on the mass of the object at the end. That doesn't matter. So it doesn't matter if it's really heavy or if it's really light. It's the length of the pendulum that determines, if you think of gravity as being fixed, it'll be the length of the pendulum that determines how long it takes. Okay. So here's the idea. We want to set up one of these. The things we can measure easily. We can measure lengths easily enough. We can measure time periods easily enough if we've got an accurate time measurement. So we can use this approximation as a way of approximating the value of g, finding what the acceleration due to gravity is. Okay? So we can imagine an experiment where somebody sets the pendulum swinging and they measure the length very carefully and they time it very carefully. Okay? But inevitably, real physical measurements are subject to errors due to inaccuracy in the way things are made, or just to inaccuracies in the way they're measured, or subtle inaccuracies in the clock that you're using to do the timing. So we'll think of the situation that we know the length is 2 meters, but to within 2 millimeters. So there's a plus or minus 0.002 meters, 2,000ths of a meter. We know the length is 2 meters plus or minus 2 millimeters. Similarly, we'll think of the time taken for the oscillation as 2.84 seconds, but let's say that's only accurate to 1/10 of a second. It could be up to 1/10 of a second either side. What's the constant? So the question here is, what is the consequences of those errors or those inaccuracies for the resulting prediction of g? How accurate will the prediction of g be? Okay, so we can set ourselves that problem. And this problem we can answer. We can get an approximate answer for it. We can estimate the error in our prediction of g by using the small increments formula. So we'll take this definition of this function here. G is 4 times pi squared times L over t squared. We can obtain the two partial derivatives. Okay. So the partial derivative of g with respect to L is, of course, 4 pi squared over t squared. You can see that here in equation 1.64. And dg dt will be minus 8 pi squared L over t cubed. Okay, because t and g is 1 over t squared, so it has the derivative minus 2 over t cubed. Okay, so we set up the small increments formula. The error in g, delta g, is approximately dg dl by the error in L plus dg dt by the error in t. And we will want to estimate the absolute value of this. We want to get a bound on the absolute value. Predict the worst that the error in g can be. So delta g is the error in g. Value it has minus the value it has at the base point to 2.84 compared with, or the difference between the value at the base point with the value at the extreme, if the L and T had the biggest error that they might have. Okay, so we say the absolute value of delta G is the absolute value of the small increments expression. We evaluate the partial derivatives, and then we use the triangle inequality. So we can say that the absolute value of that sum, because in the small increments formula we have a sum of all those terms, we just say it's less than the sum of all the individual terms. Less than the sum of all the individual absolute values. So we have 4 pi over t squared. That's all positive stuff. We don't need absolute value signs around it. But the error in L, we'll put absolute value signs around that. The minus 8 pi squared L over t cubed becomes plus 8 pi squared L over t cubed. And L and T are positive quantities, so all that's positive. And then we have absolute value of delta T there. So then we just evaluate it. Evaluate it where? Well, we feed in the base point values for L and T. So we put in L equals 2 and T equals 2.84 into this expression. And for the absolute value of delta L, we'll have 0.002. Okay. So that's the bound on the absolute value of delta L. And the bound on the absolute value of delta T, the error in T, will be 0.01. Okay, so you feed in all those values, and we get an upper bound of 0.079. So we can say that this experiment to approximate the acceleration g due to gravity, given those errors in measurements of L and T, the approximate worst case is that we have a value of g that's accurate to within approximately 0.08 meters per second per second. Okay? So that allows us to predict the error or estimate the error given errors in the inputs into the thing. Okay. So, any questions about that? Or I'll get you doing an actual example shortly. And we'll look at the second example in the notes now, and then we'll put a problem up on the board that we can work through. Second problem talks about looking at the resistance of a section of wire, a section of conductor, some metal conductor of electricity in a cylindrical shape, say. Okay, so a piece of wire. Now, again, from the physics, from the electronics, you can say that the resistance of a cylindrical piece of wire is given by this expression here, rho L over A. That P-looking thing, that's the Greek letter rho, lowercase rho, equivalent of R. Okay, so it's using rho because rho stands for the resistivity of the material. So this is a measure of the inherent resistance to the flow of electrical current that's attached to the material itself. Not depending on the shape of the material or the shape of the wire, the dimensions of the wire, but just attached to the material the wire is made from. So typically copper wire for conducting electricity. So copper would have a certain amount of resistivity. But the other aspects of the wire that affect its resistance are its length and its area A. A is the cross-sectional area. Okay. So you appreciate the idea that the longer the piece of wire is, the harder it is for electricity to flow through it, the more resistance it has to the flow of electricity. Okay. The electricity has to push its way through the wire. So that's why L, the larger L is, the larger the resistance R will be. The cross-sectional area of the wire, well, the larger that cross-sectional area is, well, that's in the denominator. So the larger that is, the smaller the resistance of the wire will be. Okay. Put in very extremely naive terms, the larger the cross-sectional area, the more room there is for the electricity to move about and pass through the wire. It's extremely naive explanation of what's going on, but it's got some correct feeling to it. So that the smaller the cross-sectional area, the thinner the wire, the more resistance it has. Okay? Puts up more resistance to the flow of electricity. Whereas the wider, the thicker the wire, the larger the cross-sectional area, the easier it is for the electricity to flow through. So the kind of problem we're going to set up here is, using the small increments formula, can we estimate what the change in resistance is going to be, the change in resistance of the piece of wire is going to be, if, let's say, for instance, the cross-sectional area were to decrease by 1% and the length were to increase by 2.5%. So we've got small variations in the parameter, in the variables, and we're looking at estimating the effect of those on the function R. R is a function of L and A. There's a fixed constant rho in there as well. Looking at estimating the change in the value of R. So again, we can pass to the small increments formula. So delta R, the change in resistance, will be approximately dr dL by delta L plus dr dA by delta A. Now, what are the changes? Well, the changes delta L, we're told L is increasing by 2.5%. So the actual change in value of delta L will be that multiple of its current value L. So delta L gets replaced by 0.025 L. And similarly, we're told the cross-sectional area is decreasing by 1%. So its change is going to be a negative 0.01 A. Okay, negative 1% of A. That's the change in the area. And positive 2.5% of L, that's the change in delta L. Delta L, change in L. The partial derivatives, yeah, we get pretty easily from the definition of the function. So R is rho L over A. So the derivative with respect to L is just rho over A. and the derivative with respect to a is rho L over, sorry, minus rho L over a squared. Because a is in the denominator, 1 over a. When you differentiate it, you get minus 1 over a squared. So the minus signs cancel out, and we're just left with this expression here. So this time we're not talking about particular base points, because we're talking about percentage changes. But you see, we've got a factor of L, you know, in total in the first term there, you've got rho L over a, and in the second term, you've got rho L over, well, rho LA over a squared. So the a's cancel to leave you rho L over a in the second term as well. So you can see the presence of the resistance in both terms of the summation in the second last expression here. We've got 0.025 times R plus 0.01 times R. So that can be expressed as 0.035 times R, just adding the coefficients together. So delta R, the change in R is approximately, so it's an approximation, it's coming from the small increments formula, approximately 3.5% of R. So we can say the resistance is going to increase because it's a positive quantity, increase by approximately 3.5%. So again, it's just showing another location or place where we can see a role played by the partial derivatives. And it's coming from this, which, think of functions of a single variable with their Taylor series. So they can be approximated by a constant, they can be approximated by a line, they can be approximated by a quadratic curve. The coefficients there all come from the derivative of the function. Now here, we will look at the full-blown Taylor series for functions of 2 or more variables pretty soon, but for now we're just focusing on the linear case. So just like the straight line case for a function of a single variable. Well, for a function of more than 2 or more variables, we get a small increments formula like that. Okay. So it's the change, the linear dependence on the change in value of a variable, and the coefficient of the linear dependence is coming from the partial derivative with respect to that variable. Okay. So here's the question we'd like to solve now. It's kind of a geometric one. So we're dealing with a torus. Get rid of some of that. Oh, no, just go there. We're dealing with a torus. It's this kind of shape here, like a donut shape. And there's 2 aspects to the donut. There's the point in the middle, which isn't on the donut, which is the point in the middle of the region. And from there, we can measure 2 radii. So we got this, the smaller of the 2, which is little r. That's just the distance from the middle within the donut, from the space in the middle out to where you first hit the side of the donut. And then large r is the radius from the middle out to the outer edge. So those 2 measurements characterize how big the donut is. And, well, using integration, you can establish this volume formula. So the volume of the torus can be pi squared over 4 times the square of the difference in the radii times the sum of the 2 radii. Okay. But what I'd like you to find now, using the partial derivatives and similar to what we just saw, is to think of both radii increasing by 1%. What kind of an effect is that going to have on the volume? It is going to make the volume go up, yeah. So you're going to make the donut thicker and expand the radius of the circle shape it's following. So the volume is going to go up, all right. But, well,
because the difference is 1 each time, and you square the difference. So, no, I don't really see it.
It's, well, I think what you're expressing is it's kind of hard to, it's not immediately obvious what the increase is going to be. Because it's a complicated formula. There's the square of the difference times the sum of the 2 quantities. So if both quantities are increasing by 1%, how is that going to, okay. So, Friday afternoons, you got to stay active because otherwise it's too sleepy. So, the first thing you got to decide on is what your small increments formula is going to look like. It's really just a matter of writing it out in this context. Well, the function is v of r and r, given by that formula there on the board. So the small increments formula is going to look like this expression delta v. The change in the value of v is approximately, and I've got the variable names, it's going to be dv d large R times delta large R plus dv d small r times delta small. That's your small increments formula that you got to work with. Okay. So feel free to work together on it, compare answers and compare approaches. Feel free to ask any questions you might have. Yeah, well, I mean, yes, you're saying you can calculate it exactly. But what we're interested in here is exploring the role of the partial derivatives in providing approximate answers. Okay. Yeah, but ultimately, who cares about this? We don't really. What we care about is working with the partial derivatives and getting to know them and getting a feeling for this small increments formula, how they provide linear approximations to the change in value of a function. So feel free to ask any questions you might have. We'll go through the answers before the end. If you have any questions about examples we've just been looking at, or any of the material up to now, it's a good time to. That's a good time to get some assistance. In the tutorial later today, or with your one next week with Stephen, depending where you are, in exercises 1.2, there's a whole bunch of examples about applying the small increments formula. So. Should be obtaining those partial derivatives. dv d large R, dv d small r. For putting them into the small increments formula, identify what delta large R and delta small r are, like the one in the resistance one, talking about percentage changes. And then trying to simplify it all out, trying to factorize delta v to see the presence of v in there. Look at what this rubbish is.
That's the time. You ask them, you ask them, the last one. You spend out and get half a cube. Then you get half squared. You get half squared bigger. You get a half cube.
Sure.
Then
So you're evaluating it at
minus
2
R
points.
big R, yeah?
Yeah, well, that's only minus
Yeah, you large. Yeah, but of course you're only. Yeah, okay, but you see, you're gonna find the exact change in value towards this radius. Like you gave yourself these figures, didn't you?
Yeah, they're examples.
They're examples,
What
yeah.
we saw the percentage change.
So you can calculate the percentage, so you can write down the percentage change, but you can also work in general. You could just say,
No, we say that the change between
I don't think it'll change.
the change between each of them.
When you do the new idea.
The
if you can, yeah, okay, if you could show that.
You get what
yeah.
I'm saying? So
Yeah.
A was 1, and B was 2, B chose 2. That's
Yeah.
so much easier than doing it that way.
Well,
So,
yeah,
think about it, but
it's-
it's typing in a calculator.
Yeah, yeah, but you're not using the Russian list.
Oh, right, yeah, of course.
That's the point.
Yeah.
Agreed. Who cares about this course? The point is to get to know them.
Yeah.
There are 6 things here. You do only one of them here. So you should have 5 there. There's 2 of this and 1 of that. And this term here, yeah, you'll put this one. R squared out. Which term? What's your one of this? Your 6 term. So you got this 2 R squared.
Yeah, I got
R
half.
squared.
But that's actually
That's a mini R squared. Big R squared. Yeah, 16 is yeah, I can calculate that. You get this, right? You get this. You get 3 times now. Add it to- That's just that line.
I will scan them and put them in. Okay, so if we look at the solution to this, I appreciate you might have got it fully out because, okay, the function's a little bit complicated. So when you find the derivatives and you put them into the small increments formula, and you put in the percentage changes, so delta large r is 0.01 large r, delta little r is 0.01 little r. You put in those changes multiplied by the partial derivatives when you found them. And you want to try and factorize that expression to see the presence of the v, because you're hoping that it's going to come out as just some constant times v, and then that constant you'll be able to get the percentage change out. So you can get the computer to do it as well. This is it, how I solved it with Sage, but of course you can get MATLAB to do this as well. MATLAB can do symbolic differentiation as well with the diff command. So using the diff command, you can do symbolic differentiation. So you can set up a symbolic formula with these two variables and get MATLAB to carry out the differentiation, and it can do factorization as well. So what we do here is I set up the two symbolic variables, large r and small r. I input the function, pi squared over 4 times the difference squared times the sum. So there's the volume function shown here. Then I set up the expression delta v, which is the derivative diff v large r times the percentage times 1% of large r plus diff v little r times 1% of little r. Okay? So I get this expression delta v, which is shown here. and it's kind of long. There's loads of terms in it, loads of polynomial terms. So I then get this thing change. So change is, I take the, see, it's still representing delta v as a function, but if I do delta v evaluated at large R and small r, it just gives it to me as an expression. So not a function anymore, but just a symbolic expression in large R and small r. So there we can see the change. So this is what you get as the change. There's a lot of stuff added together. You might have to think about, well, where is v in all of that? Can you factorize all of that? Bring it together as some multiple of v. I tried simplify, that didn't work. So the command here to use was factor. So I can just get it to show me factor of change. So the command factor change factorizes the expression change as much as it can. And it factorizes like this. 3 over 400 times pi squared times r plus r times the difference r minus r squared. So you can recognize v, because if you compare that with v here, we use pi squared over 4 times the same expression in r and r. Okay? So we did have pi squared over 4. Now we have, so instead of instead of 1/4, we now have 3/400. So we've had to multiply v by 0.03. Isn't it? At 3% change. If I divide that expression change divided by 0. Divided by 300ths, it should just give me exactly v. Yeah. So when I divide it by 3%, I get back to exactly v. So there's been a 3% increase in v. Okay. So this delta r and delta small r produce an approximate 3% increase. 3% increase in the volume v. Okay, so you might have got to the middle stage there when you get the long expressions, but then you have to think about, oh, I have to factorize these back again. I mean, it's not hard, you can do it. We just have to pick out the square factors and that intelligently. Okay, so do have a look at the MATLAB diff command, symbolic factorization, and search around the other commands as well, symbolic factorization, factorizing symbolic expressions and that. So you could get MATLAB to do this analysis as well. Or indeed, make use of Sage. I'll post this Sage sheet into the comments as usual. And so for the tutorials, then you've got lots of problems to work on in exercises 1.2.